All right. Just waiting for the streams to start. All right. And it looks like Twitch is started and there's YouTube. Excellent. Good morning, everybody, or evening, whatever it is, wherever you are. Hi, Jer. Oh, thank you. I just got a notification that Kaggle went live. Helpful information. We are jumping back in with this paper, starting with section 5.6. Hi, Juan. And just a little bit of a refresher, because it has been a week. So this is a paper out of OpenAI, and they are looking at generating sequences. And those sequences include images, hi Ali, music, and the music is in the blog post here if you want to listen to it. I haven't figured out how to manage audio so you can hear my computer audio, but only the audio I want you to hear, and not like my 5,000 Slack pings that are constantly just screaming at me. So that's the first link in the paper, and you can check that out if you want to hear the music. And also they mentioned that they did text generation, and I have been digging around on the internet, trying my very, very best to find any examples of the text that's been generated by this model. And they mention it in the blog post, but there's no text in the blog post. And then they mention it in the paper, but there's no text samples in the paper. So I guess we take their word for it that it's good. That's common in NLP, just to not show any examples of the text you generated. It's not. It's a little bit weird. To be fair, this isn't really an NLP paper. It's more of a machine learning model architecture paper. But that is, so far, my biggest complaint. And the difference between the sparse transformer and the regular transformer as proposed by Vaswani et al. Is that in the regular transformer, each token includes attention to all other tokens in the sequence, whether that's pixels in a photo, that's what those are called, pixels in a picture, or words in a text string, or thinking about it, I don't think they're going to talk about it, but I think what they're probably doing for music generation is just taking sort of the waveform at each sampling time point. So that sort of like little spectral slice. Again, hopefully they'll talk about it in the paper when they talk about generation. And then the two ways that they have modified, happy Id. The two ways that they have modified this fully attentive network is they always look at the previous C, I believe, was the variable they used for that tokens. And then in one model, they also have sort of like a trailing sample, where for every nth token they'll also look at n-5, n-10, n-15, where 5, 10, and 15 are 1, 2, and 3 times c, whatever that constant is that you specify in the model. And then the other option is that you always look at the, so once you're at the 6th item, you always look at the 5th item. Once you're at the 10th item, once you're at the 11th item, you always look at the 10th item, and so forth. So this is fixed, which sort of models column attention, and this is sparse, which is kind of like skipgrams intuitively. And the reason that they did this column thing is because when you look at the, it's evening in Portugal, I'm pretty sure, trying to do the math. Or like afternoon. When we look at the attention patterns from the full transformer model, we see that there are sometimes these patterns where attention, so here the white pixels indicate attention. The white pixels are forming both columns and rows, so that fixed pattern is designed to sort of mimic that attention pattern. I can keep saying pattern and attention in different orders all hour. And the reason that they can generate really long sequences, the benefit of this is because if you don't have to hold all of your attention units in memory, your memory size is much smaller. So I believe that the reason that they can generate longer sequences here is not because of sort of the pattern of attention, but rather that it's the things that you're ignoring that are more important, because if we don't have to hold all the light gray squares in memory, we can use the same amount of memory and cover more items in a sequence. So that's the whole thing. And then in the previous 2 weeks, we walked through the math for that. And I think we are almost done with sort of the model specification part of the paper. So we just have this discussion of mixed precision training, and then we'll talk about their training and go through their experiments. Hello from Nepal and Siddharth. Hi. All right. So let's kick it off with section 5.6. Mixed precision training. We store network weights in single precision floating point. That's like to 10 decimal points, right? Right? But otherwise compute network activations and gradients in half precision, as in Missy-Kavicius, oh, that looks like Greek. Missy-Kavicius et al., 2017. This accelerates our training due to the use of tensor core operations on the V100 GPU. What the heck is half precision? Half precision floating point. Yes, please. A binary floating point compute number format that occupies 16 bits in computer memory. Binary 16 as composed to full precision, which is, 32 bits. Okay, so this is the number of bits they're using to store each of the network weights. So the network weights are 32 bits per weight. And then the activations and gradients are stored in 16 bits. Okay, so it's just like Unicode 16 versus 32, neither of which you should use. Use UTF-8, please. Okay, this accelerates our training, blah, blah, blah. During the gradient calculation, we use, I was like, there's no verb there. We use dynamic loss scaling to reduce numerical underflow, and we communicate half precision gradients when averaging across multiple GPUs. When sampling, we cast the queries and keys to single precision, as the query key product can sometimes overflow the max value of half precision. Okay, so if you remember from the Viswani paper that we read like a minute ago, it's in the Kaggle reading group playlist if you want to go back and watch those videos. Queries and keys are both learned, so this isn't like in a database where these would be set values you would store. Those are being updated. So it's more important that you can handle a range of values there. What is dynamic loss scaling? Tell me more. Okay, so definitely something that NVIDIA supports. Did they say what GPUs they used? The V100. Okay. Dynamic loss. Dynamic loss scaling approach leads to following high level blah, blah, blah. Okay, the basic idea is to start with a large scaling factor. Let me zoom in for y'all. A large scaling factor, and then reconsider it in each training iteration. If no overflow occurs for a chosen number of iterations n, then increase the scaling factor. If overflows occurs, skip the weight update and decrease the scaling factor. We found that as long as one skips updates infrequently, the training schedule does not have to be adjusted to reach the same accuracy. Okay, so this is just sort of like you take big steps at first, and then as you get closer, you take smaller and smaller steps, and then somehow overflow plays into it. Ryan says it's a trick to make it not unstable at the beginning of training with the reduced precision. Oh, I see. So because it's half point, rather than full point, you have like less, it's like only having only having centimeters on your ruler. So being able to pick the scale in each update helps you deal with that, is what I'm getting from that. Okay, I think I've heard this and did not store it in my, I think I've heard of this and did not store it in my brain as dynamic loss scaling. Clinton said, wow, this is how engineers are made. Cheers, Rachel. Oh, thanks, Clinton. Okay. So that is their mixed precision training. Okay, so this is probably for more memory management and to make it even more efficient, because the big thing in this paper is all of the changes that they're doing and all the little tweaks and stuff is to make the trained network as small as possible, so that it scales better with the number of items in your sequence. All right, training. We use the Atom Optimizer with a linear warm-up of 5,000 iterations and gradient clipping of 1, both of which we found important for model stability. Oh, okay. So these are these are some of those parameters that you would want to make sure that you use the same values that they did. They are suggesting. Siobhan, welcome. And hello from Egypt. Hello from the United States. Ryan says, it's specific to this reduced precision stuff. People did studies trying to compress models by reducing precision. Originally, people thought you could only do inference at FP16 and not training. Oh, interesting. So it would only work for inference rather than training, because at inference time, it's easy to sort of cut down bigger things. But if you cut down bigger things during training, it's harder to extrapolate them during inference. But then people came up with some tricks to make half precision still converge. Interesting. Nirant says, what does model stability imply here? My guess is that they are referring to like a variety of the things like exploding gradients, non-convergence, that sort of general thing, and that things get a little hairy if you mess with these too much. All right, we use a weight decay penalty of 0.01. We annealed the learning rate according to cosine decay, as in Radford et al. 2018, which I think we read. We train on 8 V100 GPUs unless otherwise noted. All embeddings are of a constant dimension D, usually one of 256, 512, 1024. Nirant says this has to do with training stability, not inference. Yes, that's how I understood it. By default, all linear transforms are to the same dimension, with the exception of the feed-forward network, which projects the input to 4D, unless we use half-size transformation where it is 2D. Additionally, sometimes we have the size of the query and key transformations. Okay, so this is just like technical details that I don't think are that interesting, but if you were trying to re-implement this, would be very important for you. We initialize the token embedding WE from, what does this mean? Big fancy N, 0, okay, so this must be normal distribution, would be my guess. So a normal distribution with a mean of 0 and a variance of 0.125 divided by the square root of D. Hello, Ryan, welcome. We are sort of in the middle of this paper, so feel free to ask questions if you are a little bit lost. Okay, and I'm assuming the fancy N means normal distribution. Yeah, thank you for, what's the word I'm looking for? Confirming that for me. Within the offension, and position embeddings are the same, except the deviance is going to be a little bit bigger because it's the number of dimensions times the number of embeddings, maybe? Within the attention and feed-forward components, all biases are initialized to 0, and all weights are initialized from n normal distribution with a mean of 0 and standard deviation of this square root dimension of the indexes? Is the fan-in dimension. Fan-in dimension? Variance, normal distribution with mean standard deviation. Thank you. Normal or Gaussian. Yeah, I don't know. I must have seen that notation before somewhere, but I don't remember it. Fan-in dimension. What is fan-in? Fan? Okay, this only occurs once in the entire paper. I have no idea what that means. Mahesh says fan-in would be the number of inputs to the neuron, right? Oh, okay, that makes sense. I don't know why it's called fan, though. And Josh is confirming that fan-in is number of inputs to a neuron. Okay, so in your classic diagram, it's the number of lines going into one of your little nodes. The connections look like a fan. Oh, I can see that. Interesting. This is terminology I've never heard before. I'm learning something. The weight matrix for the output logits was initialized to 0. Okay, so these are just sort of housekeeping details, how they set up their training. Again, important to know if you want to replicate the results, and for me, not super interesting. All right, section 7, experiments. Oh, and Yahoo says we have fan in and fan out. Oh, that's helpful. Yeah, OpenAI, so the research group that this is out of tends to be more machine learning focused and less like NLP focused. So this, I'm assuming, is terminology that's much more common in the machine learning research community. Mahesh says Xavier initialization also uses it, and that's how I came to know. Cool, thank you. All right, let's get into these experiments. We empirically test our architecture on density modeling tasks, including natural images, text, and raw audio. Okay. I don't think I've heard the term density modeling before, but I'm assuming that it's like modeling the density must mean that it's in like multiple dimensions, I guess. Christopher says, logic gates and electronics also use this term. Oh, interesting. A whole set of disciplines that I have not interfaced with that much. I am not a big hardware person, I'll tell y'all right now. Okay. A summary of the results is available in Table 1. I'm going to assume that they say that they do better than current state of the art. We found that, in addition to running significantly faster than full attention, sparse patterns also converge to lower error, as shown in Table 2. Interesting. This may point to a useful inductive bias from the sparsity patterns we introduced, or an underlying optimization issue with full attention. So I'm assuming that in Table 1 they're going to say that they did better than everybody else. Yep, that's what Table 1 says. The lower error is pretty interesting. All right, let's check it out. So, summary of our findings for density modeling tasks. Results are reported in bits per byte, which is equivalent to bits for dim for image task. M refers to millions of parameters. So this is the amount of memory needed to generate, I guess. This is not a measure I'm super familiar with. I would probably use I have no idea what I'd use for this. I don't do a lot of generational tasks. Number of outputs as a component can drive in a fan out. Narant says, how are these bits calculated? That's a good question that I do not know the answer to. Let's look it up. Bits per byte. Yeah, no, I don't want to know. Oh, okay, so this is a bad thing to metric ML. This is a hard thing to Google, apparently. Bytes per second, other units of measurement, blah, 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 blah. Compression? Maybe it's a measure of compression? Christopher says, is this somehow related to entropy? That would be my guess, but then why wouldn't you just report entropy? Or perplexity is another entropy-based measure that tends to get used a lot in language modeling tasks. Ryan says, those numbers aren't as good as I expected, considering that they said they were changing the scaling of the algorithm entirely. This honestly feels like them double dipping on gradient checkpointing paper. Oh, interesting. Which I don't think we read. We read the section of this paper that relies heavily on you understanding the gradient checkpointing paper, and it was not a fun time for me. You can go back and watch that video if you're interested. So people who are familiar with this measure, I'm going to say it's probably a measure of compression, would be my guess. So lower would be better. So if you can describe more bytes with fewer bits, then you can handle longer sequences and hold more stuff in memory. Jaho says yes. Okay. And they have smaller numbers for CFAR10, which is an image data set. Smaller numbers for the English Wiki 8 data set, which again, I would probably report as perplexity, but this is not my main research area. And then image data set, they also have smaller numbers, and then there is no benchmark for classical music. So they're sort of proposing a new task here. Robbie says, so hard to understand, all things going over the head, that I am right there with you. I'd say I'm getting like 80% of this paper, and 20% of it I'm just like, okay, I don't have the background for that. Okay. And then in table 2, sparse patterns showed increased speed and also better loss on the data sets where we could compare both, which may point to a useful inductive bias in the patterns we learned or an underlying optimization issue with full attention. So they're suggesting that sparsity either captures some sort of information about the images or the text more succinctly, or that there's something up with the fully attentive model that we don't know about yet, maybe. And that paper only came out in 2017, the attention paper, so it hasn't been around that long. All right, so they're saying for the ones where we could compare both, so I'm guessing that CFAR, they don't have that available. Speed and better loss. Why wouldn't you be able to know how long things took if you're training the model? And I'm assuming this is training speed and not inference speed. Yeah, time per iteration. So that sounds like training for me. So sparse attention has the best compression with fixed. So that is, you look at the 5th, 10th, 15th, or whatever item every time, and then strided, where you look at the previous 3 and then sort of like skip 3, has a little bit higher bits per byte, but is a little bit faster. Kumar says, probably they have reported the compression on a byte scale. Ratger, Oh, sorry, rather than in percentage. I am unsure. I'm also unsure. But I get that they want this number to be low, and their number is lower. And then for CFAR 10, the sparse transformer strided had the lowest bits per byte, although not that much better than dense attention. And dense attention, interesting. So in all of these, dense attention is sort of coming in between the fixed and the strided transformer, which does answer my question about why they included both. And it's because one of them was better on one task and one of them was better on the other task. And if they'd only picked one, they wouldn't have been able to say that we've got state of the art on both of the tasks that we looked at. So that answers my question that I had for myself. And then speed, the sparse transformers are faster, which makes sense because there's fewer weights. And the strided transformer looks like it is always faster, or at least for these two specific problems, it is faster. And then the dense attention is slower, and again, that makes sense. They compute more weights. Okay, interesting. So let's look at CFAR 10. We train strided sparse transformers on CFAR 10 images represented as sequences of 3072 bytes. So they take the picture and then they'll probably take different rows and put all the rows in a single line. Models have 2 heads, 128 layers, D, so the dimension is 256, half-side feed-forward network and query key projections, and are trained for 120 epochs with a learning rate of 0.00035 and a dropout rate of 0.25 until validation error stops decreasing. Okay, that seems all pretty normal to me. We use 48,000 examples for training and 2,000 examples for validation, evaluating the performance of our best models on the test set. The model achieves 2.8 bits per dim. 2.798 plus or minus 0.004 over seeds 1, 2, 3 versus the previous 2.85 state-of-the-art Chen et al. 2017. Bits per dim. I thought it was bits per byte. Okay. We also compare performance of different attention patterns in Table 2. The strided attention reaches the lowest error in the shortest amount of time, surpassing the error of dense attention at 2.82 bits per dim. Neuron says dim equals dimensions, I guess? I guess, but it's... So the dimensions here are the size of the number of pixels you feed in, where each dimension, so each pixel would be a byte. So the dimension, each unit of dimension is 1 byte, I think is what I'm getting. Although that's confusing because it makes it seem like it's the number of dimensions of the item that they're representing. So like 1 dimension versus 2 dimensions, like line versus shape. Okay, but that does make more sense, like how many bits it takes to represent each input pixel, or presumably in text it's going to be per word. AJ says, so bits per dim equals bits per byte. I think so. Okay. Text. And this is for generation. Interesting. Okay, so the paper title is about generation. But this seems to be something density modeling. So this doesn't seem to be about generation. This seems to be about how much you can compress the information in an image. It's possible that I'm just not familiar enough with this research area to be able to interpret these results correctly, but I am a little bit confused. Let's see. I'm pretty sure they have... Let's check out the images they generate. Figure 5. Unconditional samples from ImageNet 64 by 64, generated with an unmodified softmax temperature of 1, we're able to learn long-range dependencies directly from pixels without using a multi-scale architecture. I'm just going to zoom in on some of this nightmare fuel so you guys can see it nice and big. I really like this one. It's very good. That looks like something that exists in the world. Interesting. Okay, so I'm guessing it's like language modeling where you would report perplexity, but you can also use language models to generate things. And they're reporting the generation, and they're showing the things that they generated, and then this would be similar to perplexity. Oh, Nirant says bytes per dim are for images only. Bits per byte works for information compression for other tasks with sequential nature like text or music, I think. Interesting. Juhao says, if you use less bytes per dim to generate, that means better generation model. Okay. But doesn't using fewer bits per byte or bits per dim, does that mean that the quality of your generated images or text is better? Because, and I'm not super duper up on sort of the ways that people are modeling the quality of generated things, but my impression is that there's a different set of measurements at play there. I've talked about this a little bit with Wendy Kahn, who's one of our data scientists, and we're going to be, at Kaggle, we're going to be running an image generation competition coming up at some point. And I'm pretty sure this isn't the metric we're using. So I think that this is, what they're reporting seems more like a compression algorithm than a generation algorithm to me, or at least they're not reporting on the quality of the generation. They're just sort of showing some examples and being like, it's pretty good, we think. But they don't have any examples of the text, so I don't know how to assess that. Okay. 7.2, text. In order, sorry, that was my hip popping. In order to assess sparse transformers on datasets without a strong two-dimensional structure, we trained models on the... Sorry, some of you may know my doctorate is in linguistics, and language is something that I know a lot about, and I wouldn't describe it as something with a strong, without a strong two-dimensional structure. Sorry, that's just not a way a linguist would ever talk about language. Okay. You found the reading groups very interesting. Would it be possible to request an NLP paper, low resource machine translation, or linguistically motivated NLP would be interesting? Yeah, send me a message. Once we're done with this paper, I usually do a vote to pick the next one. So yeah, those sound like interesting topics to me. Nirant says, my guess is that this is a model size metric, not a quality of generation metric. Yeah, that makes sense to me. And Nikolash says, can generation algorithms be used to generate long sequences like news articles? Yeah, absolutely. I will tell you right now, if you're using neural methods, for places where they actually do produce news articles algorithmically for things like sports scores, usually they do a rule-based templatic format, because if you do it with neural networks, sometimes the network will produce something that sounds feasible but is a lie. Like it has no truth to it, but it sounds like good language. So Ryan says text data is easy. It's only one dimension. Yeah. How hard can it be? I think Ryan is being a little bit sarcastic, as am I. Jiahao says, because we want to maximize likelihood, then to make negative log likelihood minimized means lower bits per dim. Okay, interesting. Yeah, sorry, I got sidetracked. Let's head back to the paper, and we were aroundish here. We trained models on the IngWiki 8 dataset. Sorry, IngWik 8? I thought it had an extra I in here. I thought it was IngWiki 8. Anyway, which represents the first 10 to the 8 bytes of Wikipedia and contains a great degree of variability in periodic structure. Okay. We trained with a context length of 12 to 288, which is longer than previous approaches. Neuron says, how would you combine slot filling template with neural methods? Is there some prior work on that? There might be, but honestly, I think it sounds like unless you are building like, I don't know, text generation for a big company and also have a lot of time and money, I probably wouldn't try to combine the two. Yeah, that's just my personal take on that. We trained on that. Sorry, there is periodicity in language, but not generally in text. Like periodicity is in like the wave form. We trained on the first 90 million tokens and reserved the last 10 million for validation and test. We use a 30-layer fixed sparse transformers with 8 heads, D512, and a dropout rate of 0.48. We trained for 80 epochs until loss validation stopped decreasing. We used stride of 28, C32, and merged the factorized attention heads, which I believe is discussed up here somewhere where they talk about merging. Our best model reached 0.99 bits per dim. They are using this for text, though, even though someone mentioned that it's generally only used for images. Surpassing the 1.03 state-of-the-art for similarly sized Transformer XL, Dietol 2018, and matching the 0.99 of a model trained with more than double the number of parameters. Strided attention failed to do well on this data set, whereas fixed patterns were able to recover and surpass the performance of dense attention, as listed in Table 2, which we looked at before. It is interesting to me that fixed would do better than strided. Like, I don't have a reason to believe that that wouldn't be the case, but it's a little bit interesting. Additionally, during the evaluation of the test set, we modified the minimum context length the network could use by evaluating fewer tokens in parallel. Oh, okay, I just blacked out in the middle of that sentence. During evaluation of the test set, we modified the minimum context length the network could use, by evaluating fewer tokens in parallel. We saw monotonic increases in performance with more tokens, up to 12,160 out of the 12,288 tokens used for training, which suggests that the network is effectively incorporating long-term dependencies. I'm going to need a lot more evidence than that, my friend. We modified the minimum context length the network could use by evaluating fewer tokens in parallel. Minimum context length during evaluation. Oh, I see. So they had the maximum number, and then they sort of like chopped it down and saw what happened. And what happened is that bits per byte, which we want to be lower, got lower the longer the text was. We observe increased compression of IngWiki 8. I really thought it was IngWiki. Also, their capitalization here is inconsistent. With longer context, suggesting the sparse transformer can effectively incorporate long-term dependencies. Because you would expect if there was no relationship between tokens that were very far apart, then incorporating tokens that were further apart wouldn't help you more with local tokens. Interesting. And this was for the fixed width here. So I guess you could almost think of it as doing convolutions on language, where you sample every nth word, in addition to the immediate context. I feel like that could help if the fixed stride happened to fall at important syntactic boundaries. And this is also a fairly small decrease, but the trend is also pretty strong. Actually, no, I don't know that this tells us much other than being able to see more tokens helps you represent the information better. Yeah, definitely am not convinced that this network is effectively incorporating long-term dependencies. There's a lot of work on that, and that's a very difficult task, and this is not generally how you would measure that. Vipol says, are we going to discuss anything about black data sets? I don't know what you mean by black data sets. Maybe? All right. ImageNet, 64 by 64. In order to test the ability of the model to learn long-range dependencies and scale to a large data set, we train on the version of downsampled ImageNet released by Ord et al. 2016 and evaluate on the validation set. We use a 48-layer strided sparse transformer with 16 heads and d equals 52, totaling 152 million parameters. We use a stride of 128, dropout of 0.01, and train for 70 epochs, which took 7 days on 64 V100 GPUs. Jiminy Cricket. I find it interesting that they chose to use the strided one here. So it looks like their results are suggesting that the fixed transformer model here is better for text, and the strided transformer model here is better for images. But it looks like they didn't try both of them on both types of data for each of their experiments. So we don't really have enough data to make strong claims there. Necroduke says, Jiminy Cricket. Yeah. When I was teaching in grad school, I tried to train myself out of swearing when I was surprised or upset. So I have other alternatives where I would potentially use other words. It's a I don't know. It's like a bowdlerization of Jesus Christ. So for people who are Christian, that might be, something they'd be uncomfortable with. Somebody saying in a upset context. All right. Our model achieves a loss of 3.44 bits per dim, 3.437 across one row, and in comparison to a previous 3.52. Necroduke says, I say cats. Oh, that's a good one. Which is smaller. Sorry, that is less compression than they got on CFAR 10, and I believe ImageNet is much bigger than CFAR. Net size. Blah, blah, blah. 1 million. CFAR is a labeled subset. 1 million images. And then ImageNet is 1 million images of 1,000 class. Sorry, that's blah, 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 blah. Labeled subsets. Each with 10,000 images. Okay, yeah, so CFAR 10 is smaller. Anthony says, now they're testing using strided versus the fixed from before. No, they're just using scale 48, sparse transformer. They're just using stride here. They're not trying both of them. AJ says, ImageNet is larger in terms of both images per class and resolution. Helpful. Oh, that's right. Image size matters a lot in computer vision. That is not a thing you really have to deal with in text. Actually, no, that's not true. I guess the equivalent would be like amount of bytes per character. So a lot of Indian languages that are made of a bunch of combining characters can have like 8 to 10 bytes per character in the worst case. So I guess that would be the text equivalent. If you're using UTF-8 specifically, which is why sometimes people prefer UTF-32 if they do a lot of work in that language. All right. Additionally, we generate unconditional samples, figure 5, at an unmodified softmax temperature of 1 from the model. And I don't know what this comma is doing here, 1 from the model, and from one trained with twice the layers. We include here the samples from the 300 million parameter model. On visual assessment, we find no artifacts from the sparsity patterns and see evidence of long-term structure in most images. Why are we not seeing the images from the model you're reporting your results from. You trained a bigger model and then generated images using... No, I want to see the images generated by the CFAR10 model. I want to see the images generated by the ImageNet model, the little one you evaluated in the paper, and I want to see the text examples. If you're going to talk about how good your generation is, you should show the generation capabilities of each of the models you're talking about. Don't like that. Not a fan of that. If I were reviewing this paper for a conference, they would get a salty paragraph in the review about that. And like, they look fine, and they're suggesting that there's no like sort of like weird locality effects. There's no like striations due to the, sorry, they were striated, not, they're not seeing sort of like effects of the attention pattern in this bigger model that we made earlier. Yeah, Ryan says length of text is important too. 3,000 word wiki page, much different from a tweet. That's true. Although I would honestly prefer to work with longer text personally, because I think it's easier to model, or at least easier to get information out of, even though it is more memory intensive. AJ says it would be nice to see 1.5 billion parameter model to compare with GPT-2, yeah, which was by the same research group, and which they didn't release. Like, they didn't release the GPT-2 model. So, okay. Classical music from raw audio. To test the extent to which sparse transformers are able to scale to very long contexts, we trained models on the classical music dataset released by Dieleman et al. 2018. As details of the dataset processing are unavailable, we omit any direct comparison to other work and instead study what size sparse transformer we can train with increasing context size. For each sequence length, we attempted to train the largest model, which could entirely fit into 16 gigabytes V100 accelerators without model parallelism. Okay. So, okay, so if you are comparing models here, a model which could do more compression and would require less memory for a longer sequence would do better, given this artificial constraint of we have to fit it on a single accelerator. Alato says, who knows a tutorial for beginner? This course is interesting, but needs prerequisite. I would recommend Kaggle.com, Learn, Kaggle Learn. So we have a bunch of courses. If you're interested in deep learning, we've got a deep learning course. And we have also made some like little adjustments to the viewer here, so it should be a little bit easier for y'all to use. And those went live yesterday, I think. They're pretty minimal, but we've tried to improve the user experience. Kaggle. Okay. So they are generating music from this data set that they don't know much about. Overall, we found that increasing the sequence length by a factor of 4 requires a reduction in model capacity of approximately 4 square root of 4 equals 8. 4 square root of 4 is more than 8? It's like 8.48 in there? What does this mean? We found that increasing the sequence length by a factor of 4, okay, requires reduction in model capacity of approximately 4. Oh, okay. Use the approximate symbol. Listen, I'm not great at math, but I know that the squiggle equals means approximate. Okay, thus we found we could use factorized self-attention on sequences over 1 million time steps long, albeit with extremely few parameters. Okay, so they're saying because they're not using full attention, increasing the size of the length of the your input dimension that you're looking at and paying attention over does not like exponentially increase the space you need to save your model in. AJ says, to be fair, they did release the 345 million parameter model recently, so there's hope for the full one in the future. Yeah, they did eventually, after people were like, and that's the GPT-2 model. And their reason for it was, and I think we discussed this when we read the paper, was that they were worried about people using it to generate malicious text, which on the one hand, I understand. I'm glad that they thought about it. But on the other hand, you can do that with Markov chains. Like, that is an undergraduate lab exercise. So yeah, good to do the math. 4 times square root of 4 is exactly 8. Oh my god, I was thinking of the square root of 2. You were so right. Thank you, karma. The square root of 4 is 2, as we learned in elementary school, and 4 times 2 is 8. Noted. Thank you for pointing that out. I appreciate that. Thus we found we could use blah, blah, blah. Okay. Samples are available for sequences of length 65,356, which corresponds to around 5 seconds of generated audio at 12 kilohertz. Okay, so they are using a sequence where the tokens, or like the items in the sequence, are time points in the sample rate. That makes sense. The samples clearly demonstrate global coherence over the sample period. So things like, when I went and listened to the samples, like a given sample was, forte or pianissimo. It's been a minute since I took music notation. Andante is a time signature, but they were sort of like, they were either loud or quiet, or like sort of had, one level in there, and they sort of had a similar beat and rhythm throughout. Necroduke says, it's okay, I had a bigger problem today with addition. 2,000 plus 5,000 plus 1,000 equals 9,000. Is that 8,000? That sounds right. And Josh says, it's 4 times 2. It's 8. Thank you. I'm glad you guys are here. Otherwise, I'd just be staring at this confused and alone. All right. An exhibit a variety of play styles and tones, swapping from rhythmic playing to forceful. Till some samples go to our blog. Sample quality quickly degrades for greater sequence length due to reduced model capacity. That makes sense. And these are, if you haven't listened to them, piano music. So it's just like a solo piano doing or whatever pianos are like. Table 4, performance of strided sparse transformer. So again, they'd use the striding and not the fixed width for thingadoogles. AJ says, if they're benchmarking their model for compression, shouldn't they also be compare with autoencoder based architectures? That is a really good question. I would assume they should, right? And as far as I know, part of this could be due to the fact that, as far as I know, this actually hasn't been peer reviewed. In as far as I am a peer and I am reviewing it right now, I guess. Let's go to Google Scholar. All 2 versions. Yeah, these are both on archive. It hasn't been published. So these are things that maybe a peer reviewer or a couple would be able to point out to them and help them improve their paper by including relevant benchmarks. I would also ask them to probably change the title of this paper, because it feels like the only reason that they are framing it as a generation paper is because they are... So I'm not saying that they're not generating, but the fact that they're generating with a different model than they evaluated for images feels a little bit tacked on. And the fact that they have this classical music task that it appears that they're the first people that have done, where they can't compare to other models. I think they're like, oh, our generated stuff is pretty good, is their way of arguing that the quality of the models are good because they can generate for this specific model, but they're not showing generation for all of the models, even though that's what, reading the title of the paper here, you would expect them to be talking about. Yeah, so that's my feelings at this point. We're almost done. Doop, 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 doop. Sample quality, blah, blah, blah. So they can't deal with super long things. Performance of sparse transformer on a classical audio dataset. Mu law encoded at 12 hertz. What does that mean? Mu law, or approximated as U law, is a companding algorithm primarily used in 8-bit PCM digital telecommunication systems in North America and Japan. Interesting. Companding algorithms reduce the dynamic range of an audio signal. In audio systems, this can increase signal-to-noise ratio achieved during transmission. That must be why the recording sounds sort of like buzzy and staticky. Okay, so it's the thing that you do with like a telephone. In the digital domain, it can reduce the quantization error, hence increasing signal-to-quantization noise ratio. These SNR increases can be traded for reduced bandwidth for equivalent SNR. Okay, so this is the thing that causes it's not really clipping, but like compression at the top of the frequency range, which is why fricatives can be hard to understand over the telephone. So things like S versus F, so S versus F, if you're not getting a lot of high frequency information up here at the top of the frequency band, it can be hard to disambiguate those. Okay, so maybe when I said in video 2 about the quality of the audio samples was due to the encoding procedure rather than a feature of the model used. And it looks like you get, interesting. So you actually, as you increase the sequence length, your compression gets worse and your number of parameters get worse, which is in comparison to the text results, whereas you increase sequence length or context length, your compression actually gets better. Interesting. Conclusion. We introduced sparse transformers and showed they attain equivalent or better performance on density modeling of long sequences than standard transformers, while requiring significantly fewer operations. This performance is state-of-the-art in images and text and is easily adaptable to raw audio. The model demonstrates usage of long-term context. Does it though? I guess they can argue that it exists in images, because something like this is a circle-ish, and this part look like they're connected even though they're not contiguous to each other in terms of pixels. I'm gonna need more evidence for your textual claims. You can't just like, do you guys know that the skit from Portlandia where they're like, stick a bird on it? You can't just take a computer vision paper and stick a text on it. It's like, it's its own domain. There's like specific things you have to consider. And again, what my PhD is in, obviously I think it's important. Josh says, how would you, with your background, demonstrate long-term dependence? So I would probably do some evaluation on co-reference resolution. I think is probably the best long-term dependence thing. Or incorporate some sort of parsing to show that you've, encoded that structure. So since they're positioning this as a generation paper, I would probably generate text and then search within that text for evidence of, things like co-reference. So if I'm generating, let's say, a news story link thing, it's, and I talk about, Mario and Luigi went to the store, they bought pickles. I would want to see that they is a bad example. Mario went to the store, he bought pickles. I would want to see that Mario and he have agreement in terms of gender in English, assuming Mario is a dude, which I think Mario is usually a dude's name, would be one way to show that you actually are capturing information about those long-term dependencies. And generates globally coherent samples. Oh, and acknowledgements. We would like to thank Ashish Vaswani for insightful discussions on the genesis of the project, so the Transformer paper first author. We also thank Joshua Mayer and Mark Chen for helpful discussions, and Johannes Otterbach, Prafula Dariwal, and David Lunn for feedback on drafts of this paper. Nekaduk says, in CV, it's just stick a label on it. That's true. That is true. AJ says, can we do efficient net next time, or is that too imagey? I'll put it in the voting pool and see what people think. Actually, let me grab pen and paper. So there was something, there was a request for efficient net. There was a request for low resource machine translation, and I can find a paper for that. And I'm also interested in the universal sentence embeddings, which is, I think the paper was actually out a while ago. But I've run into it in a lot of contexts in the last couple weeks. So efficient net. Oh, it could be oh, I guess it couldn't be. I was going to say the word net is inefficient, and it isn't. I was looking at it with my eyes to verify that that was the case. On account of being dyslexic, sometimes I don't word good. So yeah, those are probably the three that I'll put up for vote, and I will have those on the Kaggle channel, like community thing. I don't know what it's called, like the YouTube thing, and then I'll also put it on Twitter. So you guys, I guess you could vote twice. I mean, if you feel very strongly and you want to hunt down both polls and vote twice, I'm not going to stop you. Yeah. So I would say that this is an interesting paper about compression algorithms that has been kind of misrepresented. Yeah. I think the basic idea of changing a transformer architecture so that you don't have full attention, you have partial attention and sort of like patterns within it is interesting, definitely more memory efficient, and it looks like more efficient in terms of training time as well, which makes sense because there's fewer parameters. You don't need, if you got your query, your key, and your value, you don't need 6 times your sequence length. You need a much smaller number of parameters to update. Yeah. AJ says there's also a recent one on bias and word embeddings. I forget the name of the paper, though. Oh, the one that was presented at NACL? Yeah, that's a good point. I may need to do a little bit of... So NACL, which is the North American Association of Computational Linguistics, is a big conference, and it's going on right now. And I help organize some of the live tweeting that's going on. So if you're interested, the hashtag is NACL 2019 and NAACL 2019, and people are tweeting about the papers that they're seeing people present. Yeah, and there was an embeddings. There were a couple of bias and embeddings paper there that might be relevant. Andy says, it seems there are 2 different versions of use. The large version is different, but I'm not sure if they came from the same paper. Oh, that's a good thing. I will look into versions. And Ryan says, I think we should go retro 2015 and go through tree LSTM. Oh. Yeah, that could also be interesting. Okay, well, now I have too many papers for a Twitter poll. Yeah. I'll do some digging, I'll do a little bit of reading, and I'll make some executive decisions based on the things that I most want to read. And then I'll get that poll up before next Wednesday, so we will read the new paper next Wednesday. So thank you very much for joining, folks. I hope you found this interesting and enjoyable. I think it is I think it's an okay paper. It's kind of a little bit out of my wheelhouse, so there's some things about it that I can't evaluate super well. Yeah, I would suggest some changes before revise and resubmit would probably be my personal stance as a language person based on what they talked about. But again, that's my bias and my disciplinary focus. And on Friday, we're going to be jumping back into the forum summarization chatbot post project, and I think I'm going to start setting up some sort of experimental machinery organization to figure out what exactly we want to look at and get started on that. Maybe do a little data cleaning. All right. Thanks so much for joining, and I will see you guys on Friday or next Wednesday. Bye. Oop, gotta stop the encoding.